Good afternoon, everyone. It's a great pleasure to share our research progress on deep learning compilers on this special occasion. So I'm going to present MonoNN, enabling a new monolithic optimization space for neural network inference tasks on modern GPU architectures. So this work is in collaboration with the University of Sydney and the Alibaba Cloud. And in this work, we are trying to explore a monolithic optimization space for regular-sized deep learning model inference task. And MonoNN is able to compile all operators in the neural network into a single inference kernel, or a monolithic kernel in our terminology. So to our best knowledge, MonoNN is the first deep learning compiler that can accommodate all operators into a single GPU inference kernel for minimized non-computation overhead. Okay, so first of all, I'm going to introduce the background and the motivation of this work. In recent years, we have had a significant GPU performance boost in both arithmetic performance and the memory bandwidth, especially after introducing FP16 and FP8 tensor cores. From Pascal to Hopper architecture, the flagship computing card had approximately 100 times boost in computing throughput and more than 4 times boost in the memory bandwidth. So this advancement is making per kernel execution time keep decreasing actually. And when it comes to DNA inference, a deep neural network consists of thousands of operators forming an interconnected graph where the nodes represent the computation and the edges represent the data flow between operators. And when running the inference engine will typically launch the operators one by one from the CPU, and the concurrent computation will happen on the GPU asynchronously. So back to 5 to 10 years ago, the GPU devices are not as fast as what they are today. So the GPU computation will take a relatively longer latency, thus making the CPU overhead very easy to hide. But in recent years, we have had a significant boost in the computing throughput, thus making the non-computation overhead one of the major performance concerns. The fastest GPUs we have, the shorter the per GPU latency will be, and therefore we are going to deal with a significant non-computation overhead. So faster GPUs can offer shorter per kernel latency. However, the major portion of the performance gains from the hardware improvements for regular-sized models begins to diminish as non-computation overhead becomes a notable portion of the end-to-end latency. So on two inference-oriented GPUs, T4 and A10, we are observing on average 35% non-computation overhead across 5 popular models compared to their end-to-end latency. And this trend is continuing to grow with newer and faster GPU cards. In addition, the non-computation overhead will compromise the end-to-end speed up from the GPU performance boost. For example, after a shift from T4 GPU to A10, overall there is on average 1.6 times speed up of pure kernel performance, but the end-to-end speed up decreased to 1.4 times due to non-computation overhead. And furthermore, a common neglected factor is that the CPU is usually busy with pre- and post-processing of the input and output of the neural network tasks in real-world workload. This CPU contention often further delays the scheduling and the kernel launching. For example, we measure the T5 model, the Google T5 model, inference latency distribution under different CPU pressures. And the CPU as the CPU pressure goes up, there is a significant increase in the average inference latency as well as the variance of the latency distribution. So this makes CPU interference further exacerbate the non-computation overhead. To overcome these challenges of the neural network inference on modern GPU architectures, we built the MonoNN compiler. It's a general solution that can compile the regular-sized deep learning neural network models into a single GPU, into a single GPU inference kernel, so that one can greatly decrease the non-computational overhead, and it can perform automatic performance tuning and generate code of the entire neural network model into a single monolithic inference kernel with strong inference-oriented optimizations and minimize the non-computational overhead. So among many models and baselines we tested, all existing baselines generates hundreds of GPU kernels for a single forward inference, and whereas in contrast, MonoNN is able to compile and code generate all operators into a single monolithic kernel for the models we tested. So only a single kernel launch is needed for the inference, for each inference forward. And however, exploring a monolithic optimization space is not trivial, and it actually comes with technical challenges. So in general, there are two types of operators, as we all know, in the neural network. The first one is the compute-intensive operators, such as Zhen and convolution, and the second type is the memory-intensive operators, such as the softmax, linear normalization, and many more. And the resource setting is very different between these two kinds of operators. For example, the memory-intensive operators usually use less on-chip resource allocation for each thread, but it has a massive number of thread-level parallelism to hide the memory access latencies. And on the other hand, the compute-intensive operators usually use a large amount of on-chip resources for data reuse, and usually have a relatively low thread-level parallelism because TLP is constrained by the hardware on-chip resources. However, in a monolithic kernel, all operators will be constrained by the same resource configuration because all operators are in the same kernel, and the overall TLP setting and the overall shared memory allocation should be the same. So this poses a major challenge to make monolithic kernel possible, which is the incompatible resource allocation between compute-intensive operators and memory-intensive operators. This actually makes it a challenge to make the monolithic kernel enabled. So next, I'm going to present a high-level overview of the MonoNN compiler. The ultimate objective of MonoNN is to create an efficient joint optimization space for both compute-intensive operators and memory-intensive operators. However, as we just mentioned, these operators are incompatible with each other in terms of resource allocation. As illustrated in the figure, compute-intensive operators are in red, residing in the upper left corner of the resource allocation space, enjoy high on-chip resource allocation, whereas the memory-intensive operators have disjointed optimization space over the bottom right corner of the resource allocation figure. This means within the conventional optimization space, it is infeasible to construct a monolithic kernel because of the resource incompatibility. The insight here is to push the optimization space of memory-intensive operators to a similar area as the optimization space of compute-intensive operators, and perform code generation of memory-intensive operators in a low TLP and high on-chip resource utilization while keeping the overall performance outstanding. So as a result, MonoNN enables a new optimization space that can effectively accommodate both compute-intensive operators and memory-intensive operators into a single kernel under the same resource allocation constraint. Following the principles we just mentioned, we propose several techniques. The first one is the context-aware instruction rescheduling to generate high-performance memory-intensive operator under the same optimization space as compute-intensive operators. And second, we propose on-chip resource exploitation to utilize abundant on-chip resources to further accelerate the off-chip memory access. And finally, we propose global thread barrier merging for minimize the intra-kernel synchronization overhead. Let's consider a simple memory-intensive operator y equals to the absolute value of x. It consists of 3 instructions: load, compute absolute value, and store it back to global memory. By default, it will launch a large number of parallel threads to process input tensor x, and each thread will be allocated with a small number of registers, and of the overall workload will have a very high thread level parallelism to hide the memory access latency to the global memory. And there will be a loop to iterate over the input tensor until the input data has been processed. This actually falls into the conventional optimization space where the overall workload will have a high TLP, and there will be a low on-chip resource utilization for each thread. And therefore, the default thread, the default thread to the data mapping and resource allocation is not compatible with the monolithic optimization space. In this example, all operators are pure element-wise operators, which means there is no interloop iteration dependencies. This is actually a nice feature because it allows MonoNN to explore the default schedule as well as the schedule with higher instruction level parallelism by merging instructions from different iterations into parallel instructions within the same iteration to ensure the stall-free memory access. To ensure the stall-free instruction issues. For example, in the figure, we have 2 times instruction level parallelism enhancement with halved thread level parallelism. This offers us a trade-off between a explicit trade-off between ILP and TLP, which makes it possible to find a solution to fit memory-intensive operators into the monolithic optimization space. The profiler inside MonoNN will search over the candidate instruction rescheduling factors such as 2, 4, 8, etc. to find a solution that has the best performance under the constraint of resource allocation of the monolithic kernel. And theoretically, instruction rescheduling factors, all these instruction rescheduling factors will achieve the approximately maximal overall parallelization in terms of TLP times LLP. Therefore, MonoNN will identify a schedule that maximizes the overall parallelization and optimally fit TLP into the single monolithic kernel. Now, we already have the solution for a single element-wise operator or for a subgraph consist of element-wise operators. We would also like to generalize this solution to arbitrary memory-intensive subgraphs. So, first category is the element-wise subgraph where all operators are element-wise operators. And the second, we identify contracted subgraphs in MonoNN where the subgraph contains contraction operators such as reduction. In our paper, we detailed the process of how to breaking or decompose the contracted subgraph into element-wise subgraph and contraction operators. So if you are interested in the details, feel free to reach out to our paper. And as a result, our memory-intensive subgraphs can leverage the instruction rescheduling technique to fit them into the monolithic kernel. For example, a softmax operator can be decomposed into element-wise subgraphs, 2 element-wise subgraphs, and a reduced sum operator so that each subgraph can perform instruction rescheduling as needed. In addition, to increase the parallelism via instruction rescheduling, MonoNN conducts a comprehensive on-chip memory resource exploitation to further accelerate the memory access according to the memory access patterns. The major objective here is to utilize the abundant shared memory and cache in the monolithic kernel. we identify two major memory access patterns, two major memory access patterns in each subgraph. The first one is the streaming pattern, where each element of the input tensor will be accessed once, and the second one is the temporal pattern, where each data item in the input tensor is read multiple times by its consumers, and this pattern is commonly identified as identified by the broadcast operators. So we demonstrate this using a layer norm operation as an example. So the input tensor X to the layer norm is identified as the streaming access pattern, and the gamma and the beta are identified as temporal memory access patterns due to the subsequent broadcast operators, which is the small yellow b in the graph. And MonoNN will automatically pipeline the streaming memory access with other computations. In this way, during the computation of each iteration, MonoNN will prefetch the input data for the next iteration into the shared memory buffer and overlap the computation and memory access for a lowered memory access latency. And the memory access to gamma and beta will be annotated with the last evict annotation to preserve the data in the cache as long as possible, since they are be accessed multiple times, and they will be better to reside in the cache. Finally, accommodating the entire neural network within a single kernel will introduce complex data dependency. For example, between the compute-intensive operators and its predecessor and the successors. So we need to insert global thread barriers to synchronize across thread blocks to synchronize cross-thread block data dependency. However, directly assigning global thread barriers can lead to suboptimal performance. Consider a dependency graph like this with input tensor A and output tensor E. Directly assigning global thread barriers can result in 7 global thread barriers in total in the graph. MonoNN will calculate the minimal number of thread barriers needed to ensure correctness via the longest path-based global thread barrier merging. After calculating the longest path distance, MonoNN will arrange nodes in the dependency graph into layers accordingly. Only one global thread barrier is needed between two adjacent layers. This effectively reduces the number of thread barriers in the example from 7 to 6. From 7 to 3. And next, we will briefly introduce the auto-tuning and the code generation in the MonoNN compiler. We consider a wide range of tuning factors that can be explored to make the final kernel faster, such as the instruction rescheduling factor for each subgraph and the overall TLP and on-chip resource setting for the overall monolithic kernel, and also the locality constraint for each memory-intensive subgraph. And for the compute-intensive operators, we adopt the optimization space from Catalyst for jam and convolution operators. And finally, we use a schedule-independent group tuning to accelerate the tuning and the compilation time for the monolithic kernel. So if you are interested in that part, you can reach more details in our paper. Finally, the MonoNN will perform code generation. It will generate the tuning results of all operators into CUDA code. And our compiler has been integrated with the TensorFlow as a drop-in replacement of the XLA compiler. And the TensorFlow runtime will load the compiled monolithic kernel during the inference. Finally, let's move to the evaluation of the MonoNN compiler. We benchmark our solution with a wide range of commonly used hardware, software, and deep learning models. For the end-to-end performance, MonoNN achieves on average 2 times speed up over the baselines when batch size equal to 1 on NVIDIA A10 GPU, and 1.8 times average speed up when batch size equal to 16 and 32. For more end-to-end performance benchmark on other GPUs, such as A100 and T4, we have more detail in our paper. And we also present an ablation study to dissect the mean optimizations in MonoNN and to have a better understanding of how our solutions fit into our goal. We built MonoNN base, a lightweight monolithic kernel generator that can generate single kernel for inference with many popular optimizations. We then gradually apply these techniques we proposed into it to construct an O1, O2, and O3 variant. We observe on average 5%, 6%, and 12% speed up for O1, O2, O3 optimization for the batch size equal to 1, and 35%, 15%, and 3% speed up for batch size equal to 60. And the instruction rescheduling shows much more performance gain for the batch size equal to 16 because larger input tensor shape needs higher overall parallelism. And the comprehensive on-chip resource exploitation also shows higher performance gain on larger batch sizes because for the same reason. In conclusion, MonoNN is the first optimization compiler that utilizes a new monolithic optimization space and generates all operators into a single inference kernel. And it's the first compiler that explicitly explored the trade-off between TLP and ILP. And it's actually have a new optimization space that can accelerate off-chip memory access and minimize synchronization overhead. And finally, we have proposed the techniques to shrink and accelerate the computations, accelerate the compilations of the proposed kernel. Okay, so that's all for my presentation. Thank you very much. And we are currently working on open source, and the source code will be available soon.